Hi, everyone. Welcome back. Our next speaker is Dr. Angelo Ricarte. Dr. Ricarte is a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics and the Black Hole Initiative. He completed his PhD in astronomy at Yale University in 2019 and his BA in astronomy and applied mathematics at the University of California, Berkeley in 2013. Dr. Ricarte studies supermassive black holes across the full range of cosmic, range of cosmic size scales, from the distant quasars at the farthest reaches of our telescopes to the local supermassive black hole in the Milky Way. As a member of the Event Horizon Telescope collaboration, he is an expert in making polarized images of plasma swirling around black holes. Thank you for being here today, Dr. Ricarte.
Really happy to be here, and thanks for the introduction. Delighted that there is a black hole day, but for me, every day is black hole day because I've dedicated my life to better understanding these black holes at the centers of galaxies. And I was involved in a recent upgrade to this image of a black hole at the center of Elliptical Galaxy M87 as part of the Event Horizon Telescope collaboration. And so today I'll be telling you all about how you might image these supermassive black holes and what that means for physics and astronomy. So if you're only now tuning in, a black hole is an object that's so compact, not even light is able to escape from its gravity. They're often depicted like this, with light being warped around it and this impenetrably black surface that we call the event horizon. And these come out of Einstein's theory of gravity, general relativity. And this is a theory that has succeeded for 100 years, and we're still trying to test it out and figure out any ways in which it might fail and teach us new physics. Throughout this talk, I'll be using the word relativistic a lot, and by that I mean a regime where things are moving near the speed of light, or where space is really warped and we need to take Einstein's theory into account. One measure of an object's gravity is its escape velocity, and this is how fast you need to move in order to get away from this object. An object's escape velocity is higher if it either has more mass or is smaller. And here are three spherical objects. We've got a basketball, the Earth, and a black hole, with their escape velocities written here. So a basketball, like any other object, does have a gravitational pull. You just don't usually notice it because the Earth completely overwhelms it. To get away from this basketball, you only need to be moving at 0.00004 miles per hour. And so this is irrelevant to your day-to-day life. If your brother tells you he's stuck at the park because of basketball, it's probably not talking about its gravity. It might be something else. Here we have the Earth, and its escape velocity is much higher. You need to be moving at 25,000 miles per hour to get away from it. That's much faster than I can jump. So like the rest of you, I'm stuck here on the Earth. Not everybody has the resources to get away from the Earth's the Earth's gravity, but some people do. And then finally, we have a black hole. And this is basically defined by having an escape velocity that's equal to the speed of light. And this is where something interesting happens, because Albert Einstein realized that nothing in the universe can travel faster than the speed of light. And that means that once something gets into the horizon of this black hole, that black surface, there's no way that it can come out. In order to make a black hole, you need to smash some amount of mass into a really, really small space. How small, you might ask? Well, very small. So take the sun, for example. If you want to make that into a black hole, you need to crush it down all the way to the size of a small town. And this, by the way, is clips from a video made by YouTuber Morn1514 that I really enjoy. For the Earth, on the other hand, you want to make that into a black hole, you would need to squish that down all the way to the size of a peanut. Now, this is one class of black holes called stellar mass black holes, and those dominate the number of black holes in the universe. But others can get much, much more massive. And these are the ones that I'm particularly interested in. Supermassive black holes. These range from millions to billions of times the mass of the sun. Let's see how many suns make up the mass of this one at the center of the Phoenix cluster. There's already quite a lot of stars, but in fact, we need many more of them to account for the amount of mass that's locked up in this single object. Turns out that we think this black hole has a mass of about 20 billion times the mass of the sun, which is about as massive as supermassive black holes can get. At the center of our own galaxy, there also lurks a supermassive black hole. We call this one Sagittarius A Star, or Sag A Star, if you're a hip astronomer. And what you're looking at here is a video created by the UCLA Galactic Center group led by Andrea Ghez. This is actually real data. Each of those points of light is a star that they've been tracking for about 25 years now, spanning much of this person's career. And by analyzing these orbits, you can tell that by how fast they move and how close they are, that there's an object there that is invisible to the telescope, but is 4 million times the mass of the sun. The only thing we can think of that could potentially explain this is a supermassive black hole. And by the way, Andrea Ghez, as well as another astronomer doing similar work named Reinhard Genzel, won Nobel Prizes in physics last year for doing this work, providing evidence for supermassive black holes. We believe that these black holes at the centers of galaxies are important for shaping their overall cosmic evolution, because not all of them are as difficult to find and as elusive as the one at the center of our own galaxy. Others make their presence much more obvious. Here's an elliptical galaxy called 3C 348. And what you're looking at is a combined image of optical data, what your eyes could see, as well as these plumes that are colored pink here. That's actually radio data, meaning telescopes that are observing at really long radio wavelengths. And what you're looking at are these jets coming from the very center of the galaxy that are blasting through out to, in fact, over 1 million light years in either direction. Again, the only thing we know of that could potentially do this is a black hole that's accreting from this thing called an accretion disk and spewing out these jets of matter on either side as well. Let's take a deeper look into what this is. And an accreting black hole at the center of a galaxy is what we call an active galactic nucleus, or an AGN. And the energy injected by these jets, as well as light and winds, are very important for stirring up the gas in this galaxy. So we've got, first of all, this accretion disk of gas. It's swirling down into this black hole like water down a drain. Here's that relativistic jet that's starting here, but getting launched for 1 million light years for this galaxy. By the way, this isn't actually coming from inside the black hole. I said that wasn't possible. It's actually stuff that almost made it in, but right at the very last moment got spewed out instead in directions that are perpendicular to this disk of stuff that's falling in. And then that black surface, again, is what we call the event horizon, that point of no return. We think that these black holes, these active galactic nuclei, are important for reshaping galaxies. Our own galaxy, the Milky Way, looks something like this one on the left. This is an artist's impression. We're inside of it, so we can't actually get a bird's eye view like this. But it looks something like that. It's full of gas that's condensing to form new stars. It has a nice disk. And our current understanding is that sometimes the black holes at the centers of these galaxies turn on and start accreting matter. And then as that happens, the matter around it heats up and it starts shooting out these jets, which end up stirring up the gas, disrupting that nice disk and creating a more boring, we say, red and dead elliptical galaxy on the right here. Here's a computer simulation that kind of gets that picture across as well. What you're looking at here are two gaseous galaxies. and we're only looking at the gas part. There are stars too, but they're not going to be shown if you're wondering where they are. And in this simulation, we've got two galaxies that are colliding with each other. And when that happens, the gas in these galaxies gets stirred up, and those disks become deformed. Matter starts flowing towards the center where it can get accreted onto these black holes. And then when that happens, the gas heats up, and you'll soon see that they're going to start blowing away the gas in the simulation and heating it up such that whatever's left over when this galaxy coalesces no longer has this nice disky structure. We think this is actually going to happen to our galaxy in about 4 billion years. There's another galaxy called the Andromeda Galaxy that is on a head-on collision course towards us. And that'll be a spectacular sight to behold if there are human beings around to witness that night sky. But we'd like to better understand exactly how these black holes accrete matter and shoot out these jets. And so one thing that we do, aside from these simulations on galactic scales, is to do these simulations of gas really, really close in, near the center of the galaxy where these black holes are growing. This is a sophisticated simulation called General Relativistic Magnetohydrodynamics, or GRMHD. And it's some of the most complicated sets of simulations to wrap your minds around. When you do these, you need to take into account the fact that space is warped in these areas where gas is flowing, and that time is going slower as you go closer towards the black hole compared to farther away. And it's really fun and interesting to work with. And so you could see we've got this orange disk of gas that's flowing in, as well as these jets of material that are coming out on either side. And those things that look like ribbons or wires, those are actually magnetic field lines. We think that magnetic fields thread both the disk of gas that's getting eaten by the black hole, as well as the material that's being flung out. So supposing you wanted to get a picture of this, we also have simulations that actually make a realistic image of what this would look like if you had a telescope that was able to resolve it. And our simulations give us images that may not be exactly what you expect. A system that looks like this kind of in simulation computer land to a real telescope would actually look more like this. And now it's something much more mysterious and asymmetric. It's a whole other set of complicated calculations in order to make a video like this out of that simulation. And this is called General Relativistic Radiative Transfer, or GRRT. And this is actually my personal specialty. I make images like these out of the simulation that I showed you before. And for the purposes of understanding what's going on here and interpreting the black hole image, there are lots of things I want to point out about this movie. So first of all, one of the most obvious features is that it's asymmetric now, whereas it looked pretty symmetric in the previous slide. And the matter actually is still symmetrically distributed, except one side is brighter than the other. This is due to an effect called Doppler beaming, and it's the relativistic version of the Doppler effect. The Doppler effect, ordinarily, you may have experienced in real life, which is that when something emitting a sound is moving towards you, the pitch of that sound increases, or the wavelength of that sound decreases. And then when it starts to move away from you, the pitch decreases, or the wavelength is increasing. This is why when, say, an ambulance is coming towards you, it seems higher pitched than when it starts moving away. Now, the relativistic version of this, when matter is moving near the speed of light, includes not only this, but the fact that the light actually gets focused in the direction of motion. So the fact that we see the left side brighter than the right side means that the matter is swirling towards us on the left and away from us on the right. And you'll notice this when we talk about the asymmetries of the real black hole image later. Another strange feature is this. There's this nearly perfect and static circle on the image that isn't really moving, even though you see other parts of the image swirling around. This is called the photon ring, and it's actually made of light that is orbiting around the black hole. There's this area around a black hole where, just like ordinary matter, light can actually orbit around and around in loops. If somehow you were able to float at this location and waited around a little bit, somehow not dying a trillion different ways, you would be able to see the back of your own head just by looking straight ahead of you, just with a bit of time delay, because it takes some time for the light to loop around. And then finally, there's this thing that we call the black hole shadow. This is that near perfectly pitch black region, which is the image of the event horizon, the point of no escape. When you make simulations like these, you need to take into account the fact that the path that light takes is really bendy. And in this simulation, we're building up an image on the right out of light that is moving around this black hole in a curved space-time on the left. Some of the light is bent a little bit. This is what we call the direct image. Still bent a lot more than you're used to, right, though? Normally, light travels in straight lines. But around a black hole, it's actually warping the light around, kind of like when you have a lens in front of an image. Other paths that light takes include making a full U-turn around the black hole. And that part of the image actually gets focused into that photon ring. And then there are other images comprised of the light that has made a full loop-de-loop around the black hole. And you'll see that this part of the image is an even narrower and fainter ring. And in fact, there's an infinite sequence of rings that are squished on top of each other, fainter and fainter, sharper and sharper, out of all of these loop-to-loop paths that light can take that sum up together to form this image you see here. You may have also seen this image from the movie Interstellar, which is somewhat reminiscent of this. They took into account many of the same effects. You can see the warping of the image. You can even see the really thin and narrow photon ring inside. One thing they didn't take into account, though, is that Doppler beaming effect, that one side should be brighter than the other. But I don't blame them. This is mind-bending enough to show on the big screen. So we want to make images of systems like this. And in doing so, we want to answer many different fundamental questions about black holes and their relationships with their galaxies. For example, how do black holes launch jets? Understanding the details of this will really help us understand how galaxies evolve over time, not just the black holes themselves. Another really big question is, what is the nature of the magnetic field that's threading the black hole as well as the gas? And here I'm visualizing for you two major cases of a magnetic field, two models that we would like to discriminate. And I've actually broken them down in each column. First, we've got the part of the magnetic field that's pointed towards or away from the black hole, the part that's wrapping around, and the part that's going up and down. But the thing you should really take away is that the row on top looks nice and well ordered and pretty stable, while the one on the bottom is kind of frothy and moving around a lot. These two classes are on top a magnetically arrested disk, or a MAD, and on the bottom, standard and normal evolution, or a SANE. And these are my favorite acronyms in all of astronomy. So we basically want to understand how insane is the black hole's magnetic field. We also want to know how fast these black holes spin. I'm not just talking about the matter that's flowing around it, but actually the space-time itself. There's a region around spinning black holes within which it's impossible to stay still. Even if you tried, space-time itself would move you around as it's dragged by the black hole. And then finally, is general relativity correct? This has survived many tests over the past 100 years, but this is a new regime when we make images of these black holes. General relativity has specific predictions for how big these rings ought to be and the shape that they ought to take as well. Now, suppose you want to make an image of the shadow, so that dark region inside of the ring. Let's now think about what it takes technologically. And in terms of telescopes, there's basically a fundamental law of telescopes that you need to follow, which is that the resolution element of your telescope, basically how small your smallest pixels are, is proportional to the observing wavelength of light that you're using divided by the telescope size. And in layman's terms, if you want a sharper image, you either need to use shorter wavelength light or a bigger telescope, which oughtn't surprise you. Now we're going to work with this and see what we need to come up with in order to image these black holes. On the left side, we can figure out what this is just based on how big these black holes are and how far they are away. Even though they're cosmically sized, they are, the farther you put something, the smaller it's going to appear on the sky. And so it turns out that in order to see these supermassive black holes, the resolution you need is about 1,000 times better than the Hubble Space Telescope. You need to be able to see a golf ball located on the moon. Now that's pretty difficult, but let's not give up yet. Let's see if we can work with the other things in this equation. So let's first talk about this observing wavelength. And backing up a little bit, by observing wavelength, I'm talking about where in the electromagnetic spectrum we're going to be operating our telescope. This ranges from these high energy gamma rays, really short wavelength, high enough energy to, say, damage your DNA, to gently sloping radio waves that can be bigger than you are. The human eye only sees the optical or visible part of the spectrum, which is a tiny sliver of all that nature has to offer, about 300 to 700 nanometers in wavelength. But we astronomers take advantage of this full range when designing telescopes. And for this particular problem, for seeing the shadow, it's useful to look at these sophisticated simulations. So here we're starting at 30 millimeters, and I'm going to change the wavelength and see how this image differs. Already, you can see some pretty cool stuff. We've got this accretion flow of stuff near the equator, and then these jets that are coming out. But I said we wanted to see the shadow, so this isn't quite right. If you have too long of a wavelength, you actually can't penetrate through this gas cloud. But if you go to a shorter wavelength, you're actually seeing deeper and deeper into the system. And it's at about 1 millimeter where you can finally see this black hole shadow and the photon ring surrounding it. Now you can keep going to shorter and shorter wavelengths, and the image is getting smaller and sharper, and it's fainter as well. So that might be overkill. In addition, for technical reasons, it becomes harder to make your telescope once you're talking about this really short wavelength regime using the technology that I'm going to get into later. So far, it seems like we need to get down to at least 1 millimeter for the observing wavelength in order to resolve the shadows of these systems. Okay, so now that we have two of these things known, we just need to rearrange and see how big of a telescope we need in order to resolve these black holes. Hopefully it's not too expensive. Let's see. Okay, it turns out you need a telescope with the diameter of the Earth. Yeah, that might pose some challenges. You know, in radio astronomy, we're actually really good at making enormous dishes. This is the biggest one that humanity has made so far. It's called FAST, and it's a telescope in China. The diameter of this thing is about 1/3 of a mile across, which is mind-bogglingly huge. I worked with another telescope that was similar in size called Arecibo before that one became decommissioned. And it was really crazy just being up close to this thing. But still, this is a far cry from the diameter of the Earth. Fortunately, there is a trick that we can use, a kind of cheat that's going to allow us to have a higher resolution as if we had made a telescope that is even bigger than what this is. This is called interferometry. And what you do is you take two separate radio telescopes, you have them point at the source at the exact same time, and you have them attached with cables, and you combine their data in such a way that it's as if you are using a telescope that is as large as not just one of these individual telescopes, but the separation between them. Here we replace the telescope size of an individual dish with the separation between the telescopes instead. And this will allow us to combine many small telescopes in order to make one that's functionally larger. This is one of the world's premier radio telescopes called ALMA, located in the Atacama Desert in Chile. And here you can see you can do it with more than just two. We've got a whole bunch of telescopes that can all work together to form this thing that we call an interferometer. And this now finally allows us to get into what the Event Horizon Telescope is truly made of. We still need to go from this to something that's as large as the Earth. Now, usually when you do this technique, you need to connect these things physically with cables. But there's a special technique that you can use in order to escape that limitation. This is what the Event Horizon Telescope looks like, and it's comprised of a handful of different stations located all around the world, from Spain to the South Pole to Chile to Hawaii. And the technique used in order to combine all of these together is called Very Long Baseline Interferometry, or VLBI. And this is science on a truly global scale. What you need to do is record all of the data from these telescopes that are all observing at the exact same time onto hard drives, time them really precisely using atomic clocks, and then combine that data together later in a supercomputer, so it's as if you had them connected with cables in the first place. Here's another view of the telescopes that are part of the Event Horizon Telescope. You can see there's one in the South Pole. That's a hard one to work on. Spain, Chile, Mexico, Arizona, and Hawaii. And we're still working on adding more and more stations that'll allow us to improve the quality of our images as well. Here's a picture that went kind of viral a couple of years ago. This is scientist Katie Bowman, another Event Horizon Telescope collaboration member, and she's posing here with just a fraction of the data from one of the telescopes, I believe. In fact, just for the M87 image, the amount of data required to make that was equal to half a petabyte, about 1,000 times what fits on my laptop. And in order to do this, you really need international collaboration and cooperation. This is a subset of the people that are part of the Event Horizon Telescope collaboration. This was actually made a couple years ago, so before I joined personally. And when I'm on a telecon with Event Horizon Telescope members, I can be expected to be joined by people who are having dinner in Europe, and people having breakfast in California, and some unfortunate souls who need to wake up at horrible hours of the night to make the meeting from Hawaii and Japan as well. Now, when it comes to putting this data together, I wanted to get a little bit into the details of that, because interferometry is not just like putting together a mosaic or a puzzle. And one common misconception that I hear about is that maybe each of these telescopes is only seeing a little part of the image and you just need to stitch them together like you got a big puzzle. And that's really not what's happening. In fact, the way we do this is more complicated and also much more strange and beautiful. Interferometric image reconstruction is more like trying to put together a song when you only have some of the notes. And this is a video made again by Katie Bowman. Here I'm going to be playing a song and giving you only a few notes at a time, adding more and more, and see if you can figure out what song this is, and at what point, how many keys you need in order to do that. Okay, so at the end, you know that this is the song Ice Ice Baby, but I bet you could have already guessed that from just a few of those notes. And that's basically what we're doing when we make an interferometric image. We have a few of the notes, we're trying to put together the rest, and we're hoping that we're not guessing too much. Except in this analogy, instead of putting together a song, we're putting together an image. And each telescope pair actually is giving you just one key on the piano in that previous slide. Which key that you get depends on the separation between these telescopes and also the angle that they make on the sky compared to the actual image that you're trying to make. And then instead of notes in a song, what we observe are actually called spatial frequencies of an image. It's basically the same thing, except we're looking in space instead of time. And it's also two-dimensional because we're looking at a 2D image. So you can imagine a grid of pianos here instead of just one. On the right here, this is our best guess for what this image looks like, given the number of keys or spatial frequencies we have in the middle. And this is a movie where we're going to be using the real Event Horizon Telescope data, adding more and more of these spatial frequencies and seeing what the image reconstruction looks like. One thing that really helps is that the Earth rotates. And because the key that you get depends on the angle between the telescopes, the Earth's rotation allows you to sample different spatial frequencies. In addition, as the Earth rotates, other telescopes are also going to swivel into view, and you can get more and more pairs between these telescopes that'll allow you to sample different spatial frequencies. At the very end, you can see that once all of the data is combined, you can see this ring that is the actual light emitted from plasma swirling around the black hole at the center of the galaxy M87. To give you a better sense of scale here, let's now zoom in on this image from galactic scales all the way down. Now, this galaxy is called M87. It's an elliptical galaxy. It's actually a really big galaxy, and that's because it's at the center of a galaxy cluster. And it's actually 100,000 light years across here in this image. And so far, we're looking in the visible or optical part of the spectrum. Now we've added some X-ray data from the Chandra X-ray Observatory. And now here's the Hubble Space Telescope, the sharpest that we can get in the optical wavelengths. Here's Chandra again. And now as we go deeper and deeper, the only techniques that will allow us to make sharper images is that cheat that we call interferometry. Here we're starting with one called the Very Large Array. And now we transition to this very long baseline interferometry. This is the Very Long Baseline Array. If you include more and more telescopes or look at different wavelengths, you can get sharper and sharper images. And finally, going down and down, all the way at the center, we end up with the supermassive black hole's shadow and the ring of light that was observed by the Event Horizon Telescope. Let's take a closer look at this. So here, remember that from before, when stuff is moving towards you near the speed of light, it becomes Doppler beamed, meaning that it gets brighter. And if it's moving away from you, it gets a bit fainter. So one thing we can see already is that the way that this matter is swirling, it's actually coming towards us on the bottom and away from us on the top. And we can actually combine this with the information that we know there's a jet coming out in a particular direction. And that tells us that we think that the matter here is moving clockwise and that the spin of this black hole is actually pointing away from us. Here's another visualization of scale. This is one that I enjoy from a comic that I really love called XKCD. And here you could see that it's about maybe a factor of 10-ish bigger than our solar system. But we believe that there's 6.5 billion times the mass of the sun crammed into this space. To give you a better sense of how weird this is, This is a galaxy. This is actually one of the satellite galaxies of the Milky Way. It's called the Large Magellanic Cloud, or the LMC. You could see this if you're in the southern hemisphere. If you live in North America, it's unfortunately not up for us in the night sky. But this galaxy has billions of stars. And in fact, you would need three of these, three times the stars in this galaxy to make up all of the mass locked up into this supermassive black hole that's only a little bit bigger than our own solar system. What you're looking at is really hot plasma that's swirling around near the speed of light. And to give you a sense of how hot, you are, of course, around 98 degrees. The surface of the sun is pretty hot. That's 10,000 degrees. The center of the sun is much hotter. That's where the nuclear fusion actually happens, and that's about 27 million degrees. But this matter swirling around this black hole is much, much hotter than that. We think it's about 10 billion degrees in Fahrenheit. And that's enough for all of the atoms to be easily shredded into their components of protons and electrons. Now, if you're really up to date on black hole news, you may know that this actually isn't the latest image. About a month ago, we upgraded the image with polarization data, and our latest visualization looks like this. And this new image offers us insights into the strength and geometry of the magnetic field. Now, in this visualization, what we're trying to do is convey something that the human eye can't actually see, which is that the light that's coming from these regions like here is oriented preferentially in this direction. It's not that we suddenly got a really sharp image and can now see stripes. It's just a visualization of that. But let me back up a little bit and talk about what this polarization is. So light is an electromagnetic wave, and the polarization of light describes which way that its electric field is oscillating. In this video on the left here, we've got a wave that's going up and down, and so we would say that it is linearly polarized in the vertical direction. It turns out that polarized light is actually all around us, but we just can't see it. For whatever reason, it wasn't deemed important for us to evolve as humans. But other animals, like the cuttlefish, many arthropods, famously the mantis shrimp, have evolved to see polarization, and they basically have access to an entirely different dimension of light that we're totally incapable of seeing. That is, unless you have some tools. That's why every time I buy sunglasses, I make sure to buy polarized sunglasses, because that allows me to see more than nature had intended with my unaided eyes. They're also useful for a variety of purposes. They're great for reducing glare because reflected light becomes horizontally polarized, and polarized sunglasses tend to cancel that part out. And this is a particular example from bestfishingsunglasses.com, which tells you one good reason why you might want to buy these. If you're looking with polarized sunglasses at this pond, you cut out all of the reflected light from the sun, and you can see the fish much more clearly. It's also good for, say, getting rid of the glare on your dashboard as you're driving around. Now, when it comes to the light emitted from these black holes, it's not polarized because it was reflected or passed through some filters. It was actually emitted this way. Basically, there's this process called synchrotron radiation, and the way it makes the light ends up creating light that's polarized perpendicular to the magnetic field that created it. So at 90 degrees, here we've got a magnetic field line oriented up and down. The polarization is going to be emitted perpendicular to that. And remember, one of the things we really want to understand better is what is the strength and geometry of this magnetic field around the black hole. And so by looking at the polarization, we can try and kind of backtrack the magnetic fields that created it. Here's a video that I helped make that is trying to get this point across. So here we've got a black hole with swirling plasma on the left and an image here on the right. that's going to be created out of light that's coming from this swirling plasma. The swirling plasma is threaded by magnetic fields. These are visualized here in purple. And in this particular case, they're all arranged in a circle. And it turns out we think that when the magnetic fields are weak, they're going to preferentially look like this. And that's because you can think of them kind of just going with the flow with the rotation of the matter until they get arranged in a circle. Because the polarization has to be perpendicular to that, you end up with that polarization pattern where all the lines are pointing inwards. Meanwhile, if the magnetic fields are stronger, they can develop a more radial pattern pointing outwards and buckle against the flow of the material. And in this case, you get a different pattern. For a more intermediate case, the magnetic fields may look like the spiraling pattern. And when the polarized light gets emitted by the spiral, you'll also get a spiral just pointed in the opposite way. This is now starting to roughly resemble the black hole image. And of course, I've swept many different effects under the rug. But that's essentially the gist of how we can try and understand the magnetic fields from the direction and intensity of this polarized light. And now you're basically up to date on Event Horizon Telescope discoveries. So far, we've learned that this black hole has a mass of 6.5 billion solar masses. An independent measure of this is just how wide is that ring, I forgot to mention. And there was actually some debate in the literature in terms of whether it was 6.5 billion solar masses versus 3 billion solar masses. And we landed in 6.5 billion. We also know that the rotation axis is pointed away from us, and it has magnetic fields that are strong enough to affect gas motion. It's probably this MAD case, if you remember MAD versus SANE from many slides ago. But there's still a lot that we want to know. For example, is Sagittarius A Star any different? How is the plasma heated in detail? Can we see that photon ring, that sharp feature that is characteristic of strong general relativistic effects? How fast are these black holes spinning? And do these results hold up if we just keep looking at these sources over the course of a few years? And now I'm going to go into some future plans and additional things we can do to the data with a bit of bias towards stuff that I've been working on. So one additional avenue is circular polarization. Light doesn't have to oscillate only in a plane. It doesn't only need to go up and down or left to right. It can also oscillate in a circle. Now, you may have experienced this in real life without realizing it. If you see a 3D movie, sometimes they use circularly polarized filters where you've got some light coming into one eye that's circularly polarized going clockwise versus counterclockwise in the other eye. And if you make glasses like that, the image will look the same if you turn your head. And so it's really useful for that reason. On the right here are some circularly polarized simulated images that I've made. And counterclockwise circular polarization is red, clockwise is in blue. And there's a lot to talk about here that I have no time to get into. But basically, the circular polarized images can tell us something about the twist of the magnetic field. And it'll sometimes emphasize the photon ring, which, if you've been watching, looks pretty deep blue in many of these frames. Remember earlier on, we were talking about how different frequencies or wavelengths will give you access to different parts of this black hole's accretion flow. Now that we've seen the shadow for the first time, it'll be useful for us to combine information from multiple frequencies to get a better kind of 3D view of what this accretion flow looks like. In addition, you can pick a single frequency and take a tiny step and see how much stuff is changing. And that's what I'm plotting here on the right, what we call a spectral index map. And basically, I've taken small steps around the observing frequency of the Event Horizon Telescope. If there's a big change, I've colored it blue or green. If there's a smaller change, I've colored it red. And because this photon ring, that perfect circle again, is showing up red here, that may also give us another handle into actually observing that signature of strong gravity. A question that we get all the time is what's going on with Sagittarius A Star, the black hole at the center of the Milky Way? And we very much do want to know. This source is really different. It's 1,000 times less massive, lives in a different kind of galaxy. It doesn't have a jet. And so comparing and contrasting the two systems has the potential to teach us a lot. Sagittarius A Star actually appears larger on the sky than M87's black hole, and the data has been taken, but there are additional challenges to processing these data. So first of all, the usual interferometric reconstruction techniques, they assume that the image is static, but actually the accretion flow around this black hole moves around really quickly. Because it's 1,000 times less massive, it actually moves around something like 1,000 times more rapidly than in M87s. And so we need to deal with that data really carefully. Also, there seems to be an annoying cloud of charged particles in the way that might be in a spiral arm of the Milky Way that corrupts the image. We may just be really unlucky, and if we waited 1 million years, that cloud would have moved away. But of course, we're not that patient. So we need to deal with those effects as well. In these simulations, we expect that the images move around quite a lot. These are simulated images, or simulations of what we think the black hole in M87 could look like. And from year to year, we expect that there could be some changes. We've already seen some evidence of wobbling over the past decade, not from images, because we've only processed 1 year's worth of images, but from something previous to that. Won't get into the details of that, but there does appear to be evidence of variability. And stay tuned as we record and analyze more data, because as time goes on, hopefully that image that you saw before is going to turn into a movie. One thing that would really help is if we become even more imaginative and make a telescope that's larger than the Earth. So here we're comparing how the pairs of telescopes and the different notes or spatial frequencies you get are filled in on the right as the Earth rotates. Now, one thing that would help is if we put just a single satellite in low Earth orbit, and because it can move around faster than the Earth is rotating, you're going to sample different distances and angles between pairs of telescopes much more quickly than you could if you were just relying on the Earth to turn itself. And so that'll be really useful if we're trying to make movies of these sources over time. In addition, if you've escaped the Earth, you can now build an even bigger telescope if you go really far away. And that's one way to get an even sharper image than what we have achieved so far. So this is one proposal called the Event Horizon Imager. It's made of 3 telescopes that are orbiting the Earth here. And as time goes on, their orientation is changing just a little bit, very slowly, making this spirally pattern in terms of our sampling of these notes or spatial frequencies. And so that's where I will leave you today. I hope I have taught you about what it takes to make an image of this black hole and given you an appreciation for the immense amount of collaboration and coordination all around the world that is required to make this possible. This is really an example of what we can do as a species if we all work together. So thank you, and I'm happy to take any questions.
Let's see. All right. My video won't come back up. I hope you can hear me.
Okay, yes, I can.
Okay. I got a couple questions here. All right. Let's see.
Oh, I can see you now.
Okay, yeah, it just came back. Thank you. Are there plans for trying to image Sagittarius A? And what is the orientation of the jets compared to the iconic Event Horizon Telescope image?
Yeah, so for Sagittarius A Star, as I touched on at the end, yeah, the imaging effort has been ongoing. Data has already been taken, and we're still trying to make sense of it and try and take into account additional complicating effects that we didn't have to worry about so much with M87. Now, for the jet question, if that was about Sagittarius A Star, we don't believe that there is a jet from that black hole, which is itself very interesting. And then if we're talking about M87, the jet here is oriented, mostly pointing to the right, if you're looking at the picture that I'm showing here.
Okay. Question I like to ask all my speakers is, how did you come to be doing this type of science? What were you like as a kid that got you here?
Yeah, as a kid, I was always about this nerdy, and you know, one of my earliest memories is sitting in the library in my elementary school, and I was looking at an astronomy picture book at the time, and on the very last page, it said something like, "We think there might be these things called black holes at the centers of galaxies," and it's really about at that time when evidence was starting to really mount, and it was gaining general acceptance that what we were seeing really were supermassive black holes at the centers of galaxies. Other than that, I've always been interested in science and math. I'm what you call a theorist, and so I work on a lot of simulations. And as a kid, and even still today, I enjoy playing video games and working on my computer. And so it was a natural fit for me personally.
And there's, as you were talking about all the collaboration that goes into doing this kind of work, but there's a lot of other disciplines that are also necessary. I mean, for instance, for keeping radio telescopes up and working, whether they might be electrical engineers, mechanical engineers, technicians. Can you just give us an idea of the kinds of other disciplines needed to do this kind of work?
Yeah, so at each of these individual telescopes is itself its own project, science-worthy in its own right. It's got its own team of scientists and engineers working to make sure they're up and running as optimally as possible. And one interesting thing I'm a part of is this thing called the Black Hole Initiative here at Harvard, where based on what you said, the fact that we need to work cross-disciplinary so often, we actually have an effort to get together astronomers, physicists, and also philosophers and historians to gain their perspective on the problem as well.
Oh, actually, that's really cool. All right, I have one last thing here. It says, thank you. You filled in the gaps I had with the EHT image that was published. So, some mission accomplished.
That's all I could ask for.
All right, I want to thank you so much for being with us today, Dr. Ricarte. And I'm sure everyone